Assalamualaikum, very good morning. Inshallah, today we will continue our chapter on fluid dynamics. We'll be looking at chapter 3, finite control volume analysis. Okay, this chapter we'll be looking at introduction to fluid flow, Lorentz and Lagrange description of flow, visualization of fluid flow, Kinetic equation, Bernoulli equation, and its application, and linear momentum equation, and lastly, angular momentum equation. Okay, first of all, let's look at what is fluid control volume analysis. Okay. The development of analytical description of fluid flow is based upon the expression of the physical law related to the fluid flow in suitable mathematical form. Accordingly, we shall represent the pertinent physical law and discuss the method used to describe a fluid in motion. Okay, the purpose of finite control volume analysis is to describe a fluid in motion. Okay, in this finite control volume analysis, we will be learning about three laws. Okay, first of all is the law of conservation of mass, where we're looking at continuity equation. Second law is Newton's second law of motion, where we're looking at momentum theorem. And lastly, we'll be looking at the first law of thermodynamics, which is the energy equation. Okay, we have three laws. Okay, the three conservation laws are applied to a fixed quantity of matter called closed system or just a system, and extend to a region in space called control volume. Okay, the conservation relation are also called balance equations, since any conserved quantity must balance during a process. Okay, we have for example, mass must be balanced, the momentum also must be balanced, energy also must be balanced. Balance means that if we have a part, for example, the pipe is our system, and then we have here is the entry, and here we have the exit. Okay, but the mass must be balanced means that the mass that enter at M1 must be the same the mass that come out M2. Okay, the momentum. Okay, the momentum we have also the M, momentum M. The enter also must also the same that momentum, total momentum that comes out. It's the same for energy. If you have the energy 1 that comes in, the total 1 energy also must be the same the energy that comes out, energy 2. Okay, that's the meaning of the mass must be balanced, the momentum must be balanced, and the energy must be balanced. Okay, for fluid flow field, we have Lagrange and Lorentz description. Okay, how we describe the fluid flow is by Lagrange or Lorentz description. Okay, what is Lagrange and Lorentz? Okay, Lagrange description is to follow the path of individual object. This method requires us to track position, velocity of each individual fluid particle, and take to be a particle fixed entity. Okay, alright. Lagrange states that for example, we have the same pipe here. Same pipe. Inside the pipe, we have water flowing. Inside water, we have millions or billions particles with individual position and velocity. Okay, for example, we have particle A, particle B, C, D, E, and etc. lah. Okay, you have to track every position. For example, we have here Z and its velocity. V1, we have another one, X2, Y2, Z2, and we have V2. You have to track every single position and the velocity of the fluid flow in order for you to describe the fluid motion in this system. Okay, and Lagrange description, you need to track the individual particle. Okay, for Lorentz description, we have the same pipe with water flowing. Okay, alright, so now we're looking at Lorentz description. Okay, Lorentz description, we don't really care about what happened to individual fluid particle. Rather, we are concerned with the pressure, velocity, acceleration, etc. of which fluid particle happen to be at the location of interest of time of interest. Okay, for example, location of interest. So this is the dot is represent the location of our interest at the time of interest. Okay, the dot is actually, we also call it control volume, because we control this dot. We decide the size of this dot. Okay, this area we decide it. Okay. Okay, what if you are representing the fluid in Lorentz concept? Okay, you need to determine the properties inside the control volume. For example, you want to find the pressure inside the control volume, find the temperature, the velocity, acceleration, and etc. inside this control volume. So different from the Lagrange concept. Lorentz, we find the properties of a fluid in control volume, while individual particle in Lagrange concept. So that's the difference between Lagrange and Lorentz concept. Okay, now we'll be looking at conservation of mass and the continuity equation. Okay, the continuity of fluid flowing in the system per unit of time can be expressed by the following three different terms. Okay, we want to find the quantity of fluid flowing in the system per unit of time. Okay, we have Q. Q is the volume flow rate, is the volume of a fluid flowing past a section per unit of time. Okay, for example, we have here a pipe. Here it is pipe. Okay, this is our section 1. For example, we have here section 1, and then we have here section 2. Okay, for example, if you want to find, it state here that the volume of fluid passing a section per unit of time. Okay, so you need to find the volume of fluid passing here per unit of time. Okay, so the volume flow rate means that V dot means that per time. The volume over time, the unit is kilogram over meter cubic. Okay, this is the volume flow rate. Okay, or you can write it as Q equal to V over time kilogram. Sorry, it's not kilogram over meter cubic over second. Okay, meter cubic over second. Same here, meter cubic over second. Okay, that's Q. Okay, the second is the weight flow rate. The weight flow rate is the weight of fluid flowing past a section per unit of time. The same weight volume. Before is the volume, is passing the area per unit of time. Now this the weight passing the area per unit of time. So weight is W. So W per unit time means rate dot equal to weight over time, because weight per unit of time. So we have Newton over second. And lastly is the mass flow rate. The mass flow rate is the mass of fluid flowing past a section per unit of time. Okay, so this is a section. For example, we have a section. So this is our section 1, and then we have mass here. So it says mass per unit of time. It's mass m dot equal to mass over time. The unit is kilogram over second. Okay, this is the conservation of equation, conservation of mass and continuity equation. Okay, conservation of mass and the continuity equation. So you have three. First of all is Q, and secondly is W, and lastly is M. Okay, Q is representation for the volume flow rate. W is the weight flow rate, and M is the mass flow rate. Okay. Now, what is the equation? Okay, alright. Okay, the most fundamental of these three terms is the volume flow rate Q, which calculate from the equation for volume flow rate V or Q. Okay, V, or you can write as V dot. Q or V dot is equal to A times V. So what is this V? This V is not volume but velocity. What is A? Is the cross section area. cross-section area. We have here is cross-section area times velocity. You will get the cubic over second. Okay, meter cubic over second. Is it true? Meter cubic over second. Okay. What is the unit of A? A is area. Area is meter square. What is the unit for velocity? Velocity is meter over second. So we got 2 times 1, 3 over second. Okay, that is Q, volume flow rate. Volume flow rate. Okay, and secondly is the weight flow rate. Okay, weight flow rate can be written as W equal to gamma Q. So what is gamma? We learned before gamma is the specific weight. Specific weight is equal to rho g. Okay, specific weight is equal to rho g. So you can write W dot equal to rho g Q. This is weight flow rate. Okay, this weight flow rate. The unit for weight flow rate equal to Newton over second. So is it true? Newton over second. Why? Okay, is it true? So very easy to find. Okay, so we have rho. The unit is kilogram over meter cubic, and we have G. Okay, G is the unit is meter cubic. So meter over second square, and we have Q. The unit is meter cubic over second. Okay. Alright. So we have 3. We can cancel it. Okay, we have kilogram meter second square. So this is Newton. Why Newton? It is Newton. Okay, Newton. If you calculate it using F equal to MA or M, okay, F equal to MA, M is the mass, this is the velocity, so this is Newton over second. So it's true that W dot is equal to rho G Q or gamma Q. Okay, now lastly we'll be looking at the mass flow rate. Okay, the mass flow rate is rho Q. Okay, rho Q. Okay, mass flow rate you can write it as M, small m with dot, with equal to rho times Q. The unit will be kilogram over second. Over second because it's rate. But is it true? Okay, now we know the unit for the density is kilogram over meter cubic, and the unit for the volume flow rate Q is equal to meter cubic over second. So we can cancel out the volume, and we got kilogram over second, which is true. M dot is equal to rho times Q is kilogram over second. This is the mass flow rate. Alright, so now we have look at the mass flow rate, volume flow rate, and the weight flow rate. Okay, alright, this is the table that summarizes all the equation with the names and the symbols. Okay, it's okay to not look at this. Okay, conservation of mass and continuity equation. Okay, the method of calculating a velocity of flow of fluid in a closed pipe system depending on the principle of continuity. The figure 6.1 show the portion of a fluid distribution system showing variation velocity, pressure, and elevation. This can be expressed in terms of the mass flow rate as M1 equal to M2. So what is figure 6.1? This is figure 6.1. So let's draw a bit 6.1. Here we have a surface, and then we have a pipe here. Okay, we have another pipe with with different cross section. We have it. Okay, here is from here to here. sorry. Alright, from here to here is Z1, the elevation 1. Here to here is Z2, elevation 2. Elevations mean heights. Okay, we have here velocity 1, we have here velocity 2, and then we have here, okay, we have here area 1 and we have here area 2. Why we have different area? Because the pipe is different size. We have, and then we have a different velocity because the pipe is different size. We have different velocity. Okay, all right. So we have that kind of okay. We have that kind of figure, kind of picture. Okay. Therefore, the conservation of mass is state that the mass at m1 equal to m2. So it means that mass at point 1 here is equal to mass point 2. Okay, mass at point 1 must equal to mass point 2. Okay, where the mass is equal at point 1 and point 2, it means that the mass is conserved. That's why we call it conservation of mass. Alright, we call it conservation of mass. Okay, now, as we know that mass flow rate, okay, mass flow rate is also equal to rho equal AV. Okay, mass flow rate. We also know that mass flow rate is equal to rho Q or rho equal to AV, because Q is equal to AV. Q equal to AV. Okay. Okay, the equation 6.4, the equation here. So since we know that before that mass at point 1 must equal to the mass point 2, so the mass flow rate also the same as point 1, so point 2. So M1 equal to M2 because the mass is conserved. Okay, so substitute the equation here. We have rho, the rho of water or fluid, okay, or sorry, rho of water or liquid does not change. Okay, rho equal to A1 V1 equal to rho A2 V2. Okay, we consider that the rho is incompressible, means that cannot be compressed. Okay, cannot be compressed means that the rho at point 1 is the same at point 2. Okay, the rho at point 1 at the same at point 2. So we can cancel out the rho and we got A1 V1 equal to A2 V2, and then we got Q1 equal to Q2, which means that the volume flow rate also conserved. Again, volume flow rate also conserved. Okay. Alright, so when the is conserved, okay, since Q equal to AV, Q1 is equal to Q2, this equation we call it the continuity equation. Okay, to liquid only, to liquid, because if you're dealing with gas, okay, the rho, okay, density can be compressed. Okay, density of the liquid is compressible, so you cannot use Q1 equal to Q2. Okay, this only apply to liquid only. Liquid only for steady flow. The volume flow rate is the same at any section. Okay, so we know that we have two is the same. One we know m dot is the same at point 1 and point 2. So Q is also the same at point 1 and point 2. So we have a second equation. Okay, alright. So now we'll be looking at example. Okay, using the same figure 6.1. Okay, the inside diameter of pipe at section 1 is 2, and section 1 and 2 are 50 mm and 100 mm respectively. Water is flowing with average 8 meter per second at section 1. Calculate, they want us to find velocity at section 2, volume flow rate, weight flow rate, mass flow rate. Okay, alright, how will we do it? Okay, we have here the same figure. Okay, we have the same figure. They want us to find 4 items, which is they're giving us the diameter. The diameter 50 mm and 100 mm. So diameter. So D1, we have D1 50 mm. So we change it into meter. So we will divide it by 1000, 0.05 meters. Okay, we have D2 equal to 100 mm. Remember to change the unit, 0.1 meter. And then we have, water flowing the average velocity 8 meter per second at section 1. So we have V1 equal to 8 meter per 8 meter per second. So V1 is here, V1 V1 is here. Okay, alright. So they want us to find velocity at section 2. Okay, what is the velocity at section 2? Okay, and then volume flow rate, weight flow rate, and mass flow rate. So you want us to find Q. Want to find weight dot, or you want us to find M dot. Okay, this is small w and small m, not capital letter, not a capital letter, just a few alphabets. Okay, alright. So how we find V2? Okay, we know that from the conservation of mass and the conservation of and the continuity equation, that M1 is equal to M2, Q1 is equal to Q2. Okay, so we know that Q equal to AV. So since Q1 equal to A1 V1, V is velocity, so Q2 is equal to A2 V2 from this equation. Q1 equal to Q2. Okay, alright. So A can be found. So we have D1 equal to 0.05 meters, and we have D2 equal to 0.1 meter. Okay, you need to find the area and then find the velocity. Velocity 1 is also given to us. V1 equal to 8 meter per second. So just rearrange the equation. We got A1 over A2 times V1. Okay, and then you calculate the V2. So how we find the second problem, which is Q? So very easy, just Q equal to AV. You don't need to find. You can either find A1 V1 or Q equal to A2 V2. Okay, A2 V2. Just find any of this one is the same because Q1 is equal to Q2. Okay, the third one is they want you to find the M dot. So M dot is equal to rho Q. So you need to find the Q. Okay, rho for water is 1000. Okay, rho in water is 1000. So just multiple it by 1000, and then we got M dot. And last one is the weight flow rate. W dot equal to gamma Q. So what is gamma? We know that gamma is a specific weight, rho g. So you need to find the rho. Rho we know 1000. G is 9.81, and then we need to find the Q and calculate the weight flow rate. So this is how you solve the question. Okay, how you solve this question. So you need to solve it in your homework. Okay, this question you need to solve it in your homework. So this is your homework one. Okay, show how you calculate it. Correct. Okay, you can confirm the answer from the example, from the answer given in this example, but better you do it by yourself lah. Yeah, it's much easier. It's very easy. Okay, alright. Okay, now, so we already have here. Okay, alright, the example one. Okay, now we'll be looking at the conservation of energy. The first we had looking at. Now we had done conservation of mass. Okay, conservation of mass. So in this finite control volume analysis, we have three equations that we must be looking at. First is the continuity equation. Continuity equation. Bernoulli equation or energy equation. Okay, this is energy equation. Usually we just call it Bernoulli equation. We write it as an energy equation. Energy equation, and lastly we will look at momentum. Okay, now we have finished equanimity equation. Now we will look at what is energy equation. Okay, alright. So, conservation of energy or Bernoulli equation. In physics, you learn that energy can either be created nor destroyed. So, energy cannot be created nor destroyed, but it can be transformed from one form to another. Okay, in this is statement of the law of conservation of energy. So, this proves that energy is conserved. Okay, conserved means that the same as before. The energy at point 1 here, E1, is the same as energy point 2. So, energy at point 1 is the same as energy point 2. So you must remember. So we have mass is the same at point 1 at point 2. Q is the same at point 1 and point 2. Weight flow rate is the same at point 1 and point 2. Okay, we have now energy is the same at point 1 at point 2. Okay. So this is conservation of energy. Okay, energy. There are three forms of energy that are always considered when analyze a flow in pipe problem. Okay, there are three types of flow. Which one is the first one is potential energy. Due to its elevation, potential energy is the energy of element relative to the reference level, PE. Okay, so for example, we have here point 1. So we have the elevation 1. For example, elevation 1 is Z1. So what is potential energy? PE. Potential energy is equal to, you learned it before in your class in the physics. Okay, and we will look at it later. Okay, alright. So next we will look at kinetic energy. Okay, first we have so the total energy. Okay, when we analyze energy in system, energy in pipe, there are three energy that we are considering. Okay, energy. First is potential energy. This is total. Potential energy, and now kinetic energy. Sorry, this is kinetic energy. And last one is the flow energy or work. Okay, flow energy, sometimes call it pressure energy or flow work. Okay, this represents the amount of work necessary to move the element of fluid crossing a certain section area against the pressure. The flow energy is abbreviated Fe and is calculated from. Okay, alright. Lastly, we have flow energy. This is the three type of energy involved in this energy conservation of energy problems. Okay, potential energy is, you learned it before, mg, mgv, mgh, okay, mgh or mgz. Okay, so since we are using z, so mgz. Okay, kinetic energy, half mass velocity square, and flow energy is work actually. So work is equal to, okay, since it says here that the energy is called flow work, represent the amount of work necessary to move element across a section against the pressure. The flow energy available is rated to calculate as WP over rho. So P is the pressure, W is the weight over gamma. Okay, you can write it as for less Fs. You let it Fs. So work Fs. Okay, force time the distance. Okay, force time the distance. That is the work. Okay, so we have work here, work. Okay, right. So we have here this type of the type of energy. But WFF usually represented by pressure, by unit of pressure. Since in a fluid we are using a force come from pressure. So PA. So just write W weight times pressure over gamma. So you can write as weight times pressure over gamma. Gamma is the specific weight. Okay, this is the type of work. Okay, cis. Okay, we have here to here. Okay, we also can rewrite mgz. Mg is weight, so weight times z. So if you also can write it as W V square over 2G. Okay, can rewrite it as here W V square over 2G. Okay, alright. So we have these three type of energy equation. Okay, work, as I said before, come from pressure. So the work, I written work here, also can write as pressure times area times distance, right? This is force. So force in a fluid can be found using pressure equal to force over area. So force equal to pressure times area. Okay, so you can calculate S P. You can write the equation as P A times S is the distance, so distance is L. So area times distance, we got volume. This is volume. So can write as PV. Okay, PV. V is volume. P is pressure. PV. Also can write as PV. Okay, we have different type of form of flow energy. We rather can write as force times distance, or weight times pressure over gamma, or you can write it as pressure times volume. Okay, alright. Okay, the MSW, gamma is in. Okay. Okay, alright. So you can rewrite it back V. So we know that before that, okay, weight is equal to rho GV. Okay, weight equal to rho GV. So V is also equal to weight over rho G. So we know that rho G is equal to gamma. So V is also equal to weight over gamma, and you can write it also as P weight over gamma. Okay, so we have energy equation. So we have energy equation. You write it, we get Wz plus W V square over 2G plus pressure times weight over gamma. So we get something like this. Okay. Since the weight is also the same, so you can cancel out the weight, and you will got Z plus V square over 2G plus P over gamma. Okay. Alright. So we can write here. Okay. The show is used in Bernoulli Equation. Okay. Okay, so we know that. Okay, we have here total pressure. The total energy is here. I had read it for you. Okay, since the weight is the same, so what left is. Alright, we have here. So we know that energy at point 1, as I said before, energy is conserved in the system. So energy at point 1 is energy equal to energy point 2. Okay, so we have the part looking at this picture, right? We have here point 1, point 2, we have an elevation, right? We have an elevation. Okay, this part, huh? Okay, so energy at point 1 here, point 1 equal to at point 2. See, energy is conserved. Energy cannot be destroyed or cannot be created. Okay, so we write the equation. So P1, I write equation equal to, not equal to, plus V2 square over 2G plus 1, Z1 equal to P2 over gamma plus V2 square over 2G plus Z2. Okay, this is actually the, okay, what is this actually? Okay, this is referred as a Bernoulli equation. So this is the Bernoulli equation. Okay, alright, so they become this Bernoulli equation. So what you get here is from the energy equation, energy 1 equal to energy 2 from conservation of energy. conservation of energy, and we write the equation back in the form of P, V, and the elevation form, and we got the Bernoulli equation. Okay, this Bernoulli, we call this refer as Bernoulli equation, where pressure at point 1 over gamma plus V1 square over 2G plus Z1 is equal to pressure point 2 over gamma plus V2 square over 2G plus Z2. Okay, you must remember this equation. Please remember this equation. This is very important equation that we will be using in chapter 2, sorry, in chapter 3, 4, and also 5. Okay, right? So this is Bernoulli equation, but this Bernoulli equation have a few restrictions. Okay, you must remember. Okay, there's a few restriction. Okay, what is the restriction of this Bernoulli equation? Okay, Bernoulli equation is one. This restriction is one. Valid only for incompressible flow. Incompressible flow means that liquid only, because the specific weight of the fluid is assumed to be the same at the two sections of interest. Okay, specific weight, we call it the same. Okay, there are no mechanical devices between the two sections of interest that would energy or remove energy of the system. Okay, means that no other energy involved, only the fluid only. For example, okay, we have a pipe looking like this. Okay, this pipe. For example, we have pipe here. Okay, with different cross section area. Okay, if there are pump involved here, so you cannot use the Bernoulli equation P1 over gamma plus V1 square over 2G plus Z1 equal to P2 over gamma plus V2 square over 2G plus Z2. You cannot use this one. You cannot use this equation because we have pump here. Okay, you can use here only the equation only if only no energy added devices is involved, no energy removal device is involved. Okay, and the fluid is incompressible. Okay, how to use this Bernoulli equation? So we have three restrictions, which is one, the fluid is incompressible. Incompressible. Secondly, no energy added device. Energy added device. Okay, and lastly, energy that remove device is involved. What is the energy that what is the device that remove energy? For example, we have turbine, fan. Okay, that is the energy that remove the there is a device that remove the energy. Okay, if we have energy that added and we have a device that energy to the fluid, okay, we have pump. Pump if the device that added energy to the fluid. Okay, this plus energy plus, this energy minus for the turbine and fan. Alright, this is the decision when I using Bernoulli equation that the fluid is incompressible, cannot be compressed, no energy added device is involved, no energy removal device is involved. Alright, so what else we have here? I think that's all. So I think that's all for today's class, inshallah. I will showing you a few example in tutorial. Okay, so please look at the example later. Okay, thank you for listening. Assalamualaikum warahmatullahi wabarakatuh.